We'll discuss surface chemistry today. So these are the topics that we'll go through: adsorption, catalysis, colloidal state. So in adsorption we'll discuss physiosorption, chemisorption, factors affecting adsorption of gases on solids, and there we will discuss the isotherm of Langmuir a little bit. In catalysis we'll discuss on the homogeneous and heterogeneous activity and selectivity, and we'll go to enzyme catalysis. In the colloidal state, we'll discuss the distinction between true solution, colloids and suspensions, lipophilic, lipophobic, multimolecular and macromolecular colloids, properties of colloids, Tyndall effect, Brownian movement, electrophoresis, coagulation, emulsion, and then its types. So going further, what is a surface chemistry? So we'll discuss what is surface chemistry. So surface chemistry is nothing but the interaction of fluids and gases on the surface of a solid. So whenever there is interaction of fluids or gases on the surface of a solid, then it comes under surface chemistry, because there are so many examples regarding or what surface chemistry is important at. Like for example, in the exhaust of automobiles these days, we have different rare earth metals that controls the pollution or breaks down the emission gas from the exhaust, and it breaks down into smaller molecules so that it is less harmful to the atmosphere. And so that is itself in itself a surface phenomenon. Now, what is adsorption? The attachment of a substance on the surface of a solid or a liquid is called adsorption, and the reverse is desorption. So it is quite different from absorption, because when a substance flows through something as a whole and in uniform, then it's called absorption. But adsorption is only on the surface. It's a surface phenomenon. Like suppose you dip a rock in water, you take it out, then the whole of the rock is covered with water. But if you break open the rock, then you will notice that the inside of the rock is still dry if you break open. Or if you dip a chalk in ink or a colored solvent, then when you take it out, the whole of the chalk will be covered in that color. But if you break open, the inside of the chalk is still white in color. That's an example of adsorption. Moving along, what is adsorbent? Substance that adsorbs. So suppose the stone, in the example of water and stone, the adsorbent is the stone, but the adsorbate, what is adsorbate or substrate? Substance that gets absorbed. So water is the adsorbate or the substrate. Now adsorption becomes pronounced when the adsorbent has a high surface area. That means the more is the surface area, more will be the adsorption, and it is relative. So the examples are silica gel, charcoal, etc. Like in purification of water, we use charcoal because in the charcoal filters the very fine particles in water. Even silica gel, you might have noticed this silica gel. It comes in packs. In when you receive a package, suppose there will be a small packet of silica gel, and the silica gel is colorless, but once it absorbs moisture, it turns into blue. So once it's fully blue, you again recharge it by heating it, then it becomes colorless again. That's how the adsorption phenomenon can be reversed, desorption. If you when you recharge it, we are letting it undergo desorption, and that's how the silica gets recharged, and so on. So more is the surface area, more will be the adsorbed substrate. and that's just related, it's directly proportional to the surface area. Less is the surface area, and it's logical also. Less will be the available space for the substance to get absorbed on the adsorbent. But it's hard to measure. Therefore, the surface area is hard to measure for examining or for determining the number of adsorbed particles that that gets adhered, that gets attached to the surface. So we usually relate it to mass of the substance and assume it's proportional. So types of adsorption, we have two types of adsorption: chemisorption or chemical adsorption, and physisorption or physical adsorption. In chemisorption, the chemical bonds are formed on the surface, and it has a high enthalpy change. Del H of reaction, the enthalpy change of reaction is high in terms of chemisorption or chemical adsorption. But in physisorption, we just encounter weak intermolecular forces. Suppose the example that I stated at the beginning, like dropping a rock or a stone in water, we can say it's physisorption, because once you take out the rock and leave it outside, it becomes dry. That means the water that gets attached on the surface of the rock, it goes away because it's a physisorption. There are only weak intermolecular forces that lets the water get attached to the stone. But in terms of chemisorption, when we talk about chalk tipping in ink, suppose, and so that's an example of chemisorption, because once you take out the chalk and you try to reverse the process, it's quite difficult, because the interaction between the ink and the chalk, we have a high enthalpy change, and there is a bond formation between the two, and therefore it comes under, we can say it's chemisorption. Now moving on, we have positive and negative adsorption. So what is positive adsorption? When the concentration of adsorbate is more on the surface of adsorbent relative to its concentration in the bulk. So for positive absorption, there is large deposition of the adsorbent on the adsorbate. And in negative absorption, it is quite the opposite. When the concentration of the adsorbate is less than the surface relative to its concentration, so it's called the negative adsorption. Now, one thing about physical adsorption is that by applying physical changes such as in temperature, pressure, we can reverse physisorption. As the interaction is just weak van der Waals forces, we can easily overcome it. But that's and in physical, the characteristics of physical adsorption is that the enthalpy change is just around 20 to 40 kilojoules per mole. So it has a very low enthalpy, and it can easily be affected by temperature. Once you increase the temperature, the reverse process happens. The nature of the adsorbate, state of the adsorbate, and so on. Yeah, state of the adsorbate is also important, like liquid, solid. So it differs from one to the other. But in case of chemisorption, the enthalpy change is quite high, 80 to 240 kilojoules per mole, and it's quite irreversible, and it has a high selectivity, because we have to take into account the chemical interaction that can take place between the adsorbent and the adsorbate. Once there is interaction for chemisorption to take place, once there is chemical reaction, it's very difficult to reverse it. Suppose you take the suppose when we imagine emission of gases, nitrous oxide, suppose, or yeah, from vehicles, automobiles. So once it suppose rhodium metal, we use rhodium and all, and on the surface of these metals, the nitrous oxide, it breaks down into nitrogen and oxygen. So it's quite a fast process, and so we use those for breaking the poisonous gases into less or friendly gases, as we can say that. Yeah. Okay. The adsorption process is a dynamic equilibrium. Adsorption of substrate onto absorbent is a dynamic equilibrium. So suppose see, if A in the gaseous phase A gets deposited on a solid, on the surface of a solid, then the interaction we can write it AS, and it's in equilibrium, and the enthalpy change of adsorption is, if it is less than 0, it's exothermic. If it is more than 0, it's endothermic. And once you increase the temperature of the particular reaction, adsorption goes down. So this was studied, but the effect of pressure is the reverse. Once you increase the pressure, usually the adsorption is more, and this was studied in bulk by Langmuir, and we'll try to discuss a little bit on Langmuir adsorption, etc. So to understand a little bit on Langmuir's adsorption isotherm, we will discuss what is fractional coverage. So the fractional coverage is denoted by delta, and it's the number of adsorption sites occupied over the number of adsorption sites available for adsorption. So in adsorption experiment, method is we measure the amount of gases adsorbed at varying pressures at constant temperature. So that's why it's called absorption, Langmuir adsorption isotherm. Isotherm simply means you keep the temperature constant and vary other parameters like pressure, volume, density, and so on. You, by varying other those parameters, you can, and keeping temperature constant, you can obtain the isotherm. So what we are doing here is varying the amount of adsorbate, and we are going to measure the effect on the amount of adsorbate that is absorbed, which leads to fractional coverage, that is the adsorption sites occupied, number of adsorption, and number of adsorption sites available. So if this is the equilibrium, so now once the gas gets adsorbed on the surface, that will be our fractional coverage theta, and that will be nothing but the number of moles over the number of moles adsorbed over the n infinity, which is the complete coverage of the surface of the adsorbent. Adsorbent. So which is simply the volume. The number of moles will be just the volume over volume infinity. So which is literally saying that the number of moles is directly proportional to our volume. Now, amongst the isotherms, one of the simplest is our Langmuir isotherm. So in Langmuir's isotherm, the assumption is only monolayer is considered. Suppose the deposition of the adsorbent on the adsorbate, we consider only the first layer. There is only one layer, monolayer, and all the adsorption sites are equivalent. That means the whole of the sites are considered to be equivalent, which means it's a homogeneous surface, and the adsorption of molecule into an empty site won't be affected by the pressure of other adsorbed molecules. That means when the adsorption starts to happen on the adsorbent, so the process is considered to be uniform. That means there may be vacant sites also, but we'll just consider it to be uniform. And here an equilibrium between adsorption and desorption will be established during the process. Some will get attached and some will move out. That's what the consideration is. So moving on. So our equilibrium is this. So the forward reaction is the adsorption. So we'll consider the equilibrium constant to be Ka, adsorption, and the reverse reaction, desorption, we'll consider the equilibrium constant to be Kt. And the gases will be under pressure P, and the surface available, which is our fractional surface available, will be 1 minus theta. That means we'll consider the total area to be unity, 1. And the rate of absorption from this equilibrium will establish that it's Ka P into A. Because pressure is involved, we are including the pressure here, and A is nothing but this 1 minus theta. So, and rate of desorption is Kd. This reverse rate is Kd As. So Kd should be just theta because A is just theta. And at equilibrium, these two reactions will be the same. So we're just equating it. And now doing some algebra, we can obtain the fractional constant. So this is the Langmuir, and dividing by the the equilibrium constant for desorption, we're getting the Langmuir adsorption isotherm. This is our Langmuir adsorption isotherm, and this one is an important concept for higher studies. So keep in mind. And this equilibrium constant is nothing but Ka over Kp, the adsorption over the equilibrium constant of the pressure. So variation of theta with pressure at different equilibrium constant. And the next is, again, there is another isotherm, Frendulic adsorption isotherm. We won't go through in detail, but in this isotherm also, at constant temperature, adsorption is directly proportional to the pressure. So if X moles over the mass is directly proportional to the amount of gas adsorbed per unit mass of adsorbent. So this is the mass of adsorbent and amount of gas absorbed. If we plot it, then at constant temperature, we are getting this isotherm. And in the first case, if it is at low pressure, then we can obtain the slope by this mechanism, 1 over m. At high pressure, it's just the amount of gas adsorbed over the mass of adsorbent is just equal to the reaction constant K, because P naught will be just 1. And at intermediate pressure is 1 over, the pressure is 1 over X, or 1 over N, number of moles. So to find the values of constants K and N, the rate constant and the number of moles, we employ this adsorption isotherm. So next class we'll discuss about the colloids and catalysis. So